We will continue with the next problem. A composite step shaft, as shown in figure, consists of an aluminum section 50 mm diameter and a steel section 25 mm in diameter. The ends of the shaft are fixed. Determine the maximum stress in aluminum and steel shafts. Take GS is equal to 84 GPa and GAL is equal to 28 GPa. So basically this is a composite bar with two different materials, that is aluminum and steel. And one more, there is a small mistake in the problem, that is here in the problem it is given the ends of the shafts are fixed, means both the ends should be fixed. So here in this problem only one end is fixed, so we have to just make a correction that we have to fix this end also. Okay, in the figure it is given wrong, just make a small correction that fix this end also. Okay, so now you can see 4 points here, point A, point B, point C and point D, means there are 4 nodes and number of elements are 3, element 1, element 2 and element 3. Element 1 and element 2 is of aluminum and element 3 is steel. Okay, at node number 2 there is a torque of 200 Newton meter. Okay, so basically 3 elements, element 1, element 2 and element 3. Length of element 1 is 200 mm, length of element 2 is 300 minus 200 means 100 mm. Okay, length of element 3 is 300 mm. So before writing the FEM model, we'll just calculate the polar moment of inertia J. Okay, so since there are two different materials and two different cross sections, there will be two polar moment of inertia, that is J1 and J2. J1 is equal to pi d1 to the power of 4 by 32, that is pi into the diameter of a limb, that is 50, pi into 50 to the power of 4 by 32, that is 613.5 into 10 to the power of 3. J2 is equal to pi d2 to the power of 4 by 32, that is equal to pi into 25 to the power of 4 by 32, that is equal to 38.34 into 10 to the power of 3. So next we'll write the FE model, same as explained in the previous problems. 3 elements, element 1, element 2 and element 3. 4 nodes, node 1, node 2, node 3 and node number 4. T1 theta 1, T2 theta 2, T3 theta 3 and T4 theta 4. Torsion and angle of twist respectively at node number 1, 2, 3 and 4. Length of element 1 is 200, element 2 is 100, element 3 is 300. So we'll calculate the stiffness matrix initially. Okay, the stiffness matrix for element 1 is K1 is equal to G1 J1 by L1, 1 minus 1 minus 1 and 1. 28 into 10 to the power of 3 into 613.5 and 10 to the power of 3 divided by 200. Upon solving, we will be getting 10 power 6, 85.9 minus 85.9 minus 85.9 and 85.9. Next, elemental stiffness matrix for element 2. K2 is equal to G2 J2 by L2, 1 minus 1 minus 1 and 1. Same value, but only one difference is your length. So length of element 1 was 200, length of element 2 is 100 mm. 1 minus 1 minus 1, 1. Upon substitution, we will be getting 10 power 6, 171.8, minus 171.8, minus 171.8, and 171.8. Next, elemental stiffness matrix for element 3 is K3 is equal to G3, J3 by L3, 1 minus 1 minus 1 and 1. Here the value of G, J and L all are different because this is of material steel and length is also different. 84 into 10 to the power of 3 into 38.34 into 10 to the power of 3 divided by 300. 1 minus 1 minus 1 and 1. 10 power 6, 10.74 minus 10.74 minus 10.74 and 10.74 respectively. So all these are the stiffness matrix for element 1, element 2 and element 3. Next what we have to do is we have to combine all this and form the global stiffness matrix. By adding we get the global stiffness matrix, that is K is equal to 10 to the power of 6, 85.9 minus 85.9, 0, 0, minus 85.9, 257.7 minus 171.8, 0, 0, minus 171.8, 182.54 minus 10.74, 0, 0, minus 10.74 and 10.74. So next we will be writing the load vector. Okay, 4 nodes are there. So at 4 point torsion supply T is equal to T1, T2, T3 and T4 transport. T is equal to 0, T1 is 0, T2 is 0, T3 is 2, T1 is 0, T2 is 0.2, T3 is 0 and T4 is 0 transport. Next write the equilibrium equation, that is K into theta is equal to T. This is the K matrix, theta 1, theta 2, theta 3 and theta 4, 0, 0.2, 0 and 0. So from the problem we know that both the ends are fixed, that is first end and the last end, both ends are fixed. So what we have to do is we have to eliminate first row, first column and last row and last column. Okay, that is see theta 1 and theta 4 both are 0 as I told. So by eliminating all those, what we get is we will get the remaining 10 power 6, 257.7 minus 171.8 minus 171.8 and 182.54 into theta 2, theta 3 is equal to 0.2 and 0. So upon solving this, we will be getting the value of theta 2 and theta 3 as theta 2 is equal to 2.083 into 10 to the power of minus 9 radians and theta 3 is equal to 1.961 into 10 to the power of minus 9 radians. Okay, so this is theta 2 and theta 3 values. Next we have to find the shear stresses. Shear stress for element 1, tau 1 is equal to G1 R1 by L1, 1 minus 1, 1, theta 1 and theta 2. So these are the for element 1 angle of twist, theta 1, theta 2, element 1 and element 2. So node 1 and node 2. 28 into 10 to the power of 3, 25 divided by 200, 0 plus 2.083 into the power of minus 9. So upon solving, we will be getting the value of tau 1 as 7.29 into 10 to the power of minus 6 Newton per mm square. It is 7.29 Newton per meter square. Similarly, for element 2, tau 2 is equal to G2 R2 by L2 minus 1, 1, theta 2, theta 3. Tau 2 is equal to 28 into 10 to the power of 3, 25 divided by 100 minus 2.083 into the power of minus 9 plus 1.961 into the power of minus 9. By solving, we will be getting the value of tau 2 as minus 854 Newton per mm square or minus 0.000854 Newton per meter square. For element 3, tau 3 is equal to G3 R3 by L3 minus 1, 1, theta 3 and theta 4. Substituting all the values, we will be getting the value of tau 3 as 6.86 to the power of minus 6 Newton per meter square or 6.86 Newton per meter square. So this is how we find the unknown angle of twist and the shear stresses. Next problem. A hollow circular section shaft 2 meter long, is firmly supported at each end and has an outside diameter of 80 mm and inside diameter of 63.8 mm. The shaft is subjected to a torque of 12 kN meter applied to a point 1.5 meter from one end. Calculate the maximum shear stress and angle of twist in the shaft. The shear modulus G is equal to 8 into 10 to the power of 4 Newton per mm square. So this is the hollow circular shaft we are seeing. Okay, fixed at both ends. Overall length is 2 meters, and from 1.5 meter from one end, it is subject to a torque of 12 kN meter. Okay, outside diameter is 80 mm and inside diameter is 63.8 mm. So there is only one difference when compared to your previous problems, that is while calculating the value of J. So in your previous problems till now, that is problem 1, 2 and 3, we are calculating as J is equal to pi into 10 to the power of 4 by 32. That was for a solid section. Now this is a hollow section where two diameters are there, that is a internal diameter and external diameter. So J is equal to pi by 32 d naught to the power of 4 minus di to the power of 4. That is outside diameter minus inside diameter. This is the major change here. So by solving this, we will be getting the value of J as 2.394 into 10 to the power of 6. This is the only one difference. The rest all steps are same as your previous problems. Next we write the FE model. Okay, basically it is a simple two elemental problem, two elements with three nodes, node 1, node 2 and node 3. Element 1 is of 0.5 meters and element 2 is 1.5 meter. T1 theta 1, T2 theta 2 and T3 theta 3 at node number 1, 2 and 3 respectively. So next we have to find out the elemental stiffness matrix for both element 1 and element 2 before proceeding for the global stiffness matrix. So stiffness matrix for element 1, K1 is equal to G1 J1 by L1, 1 minus 1 minus 1 and 1. G1 is 800 to the power of 4 into 2.394 into the power of 6, the value of J1 divided by 500, length of element 1. 1 minus 1 minus 1, 1. So as I have told previously, we have to do necessary unit conversions wherever necessary. 10 to the power of 6, 383 minus 383 minus 383 and 383. Next, stiffness matrix for element 2 is K2 is equal to G2 J2 by L2, 1 minus 1 minus 1 and 1. Substituting all the necessary values, only one difference is here. Length of the element is 1500 mm. 10 power 6, 127.68 minus 121.68 minus 127.68 and 127.68. So the global stiffness matrix K is equal to K1 plus K2. 10 to the power of 6, 383 minus 383, 0 minus 383, 510.63 minus 127.6, 0 minus 127.68, 127.68. Next we write the load vector. T is equal to T1, T2, T3. T1 is 0, T2 is 12, T3 is 0. Next we write the equilibrium equation, that is K into theta is equal to T. We know the value of K, theta 1, theta 2, theta 3 are 3 angle of twist, and the load vector, the torque 0, 12 and 0. Since it is fixed at both ends, that is first node and third node both are fixed, we eliminate the first row, first column, last row, last column, we eliminate it. So what will be remaining is just 510.68 into theta 2 is equal to 12. 510.68 to the power of 6, theta 2 is equal to 12. So just make one change, it is 10 to the power of 6, not 106, it is 10 to the power of 6. Just make a note here, note of the changes here. 10 to the power of 6, theta 2 is equal to 12. So upon solving this, we will be getting the value of theta 2 is equal to 0.0234 into 10 to the power of minus 6 radians. So this is your angle of twist at node number 2. Next, we have to find out the shear stresses. For element 1, tau 1 is equal to G1 R1 by L1 minus 1 1 theta 1 theta 2. So tau 1 is equal to 8 into 10 to the power of 4 into 40 divided by 500 into 0 plus 0.0234 into the power of minus 6. Upon solving, by getting the value of tau 1 as 149 Newton per meter square. Similarly, for element 2, tau 2 is equal to G2 R2 by L2 minus 1 1 theta 2 and theta 3. 8 into 10 to the power of 4 into 40 divided by 1500 minus 1 1 0.0234 and 0. This is the values of theta 2 and theta 3 respectively. Upon solving, we will be getting the value of tau 2 as minus 49.92 into the power of minus 6 Newton per mm square. It is minus 49.92 Newton per meter square. So this is how we find the unknown angle of twist and the shear stresses. So these are the problems in this chapter. Only two unknowns we are finding in this chapter, that is the angle of twist and the shear stress. For all the problems, the procedure is almost the same. No major changes are seen. So it is easy to learn this chapter and score marks from this chapter.